Hey, welcome back. So, last time we looked at number systems. So, today let's look at variables, constants, and some other things. So, we have seen this picture before. It's the Commodore 64 memory, which goes from 0000 all the way up to FFFF. And as I said before, in this case, I divided it up in 4 kilobyte segments. But as we have already talked about, in reality, it looks like this down here. So 000, then 1, 2, 3, 4, 5. So every memory cell in the Commodore 64 has its own address, starting at 0000. Alright, well, let's look at the memory another way. Let's look at it this way. So it's the same thing, only vertically. Starting at 0 down here, and all the way up to FF up here. So this spreadsheet is actually something I use when I plan my games. Because here I can plan how much space I want to use for different things. And that's something that's important that we will come back to. But we need to be aware that everything in our program or in our code takes space. Even our LDA, STA commands, all of that also takes space in the Commodore 64 memory. But variables, what's that? Well, last time I mentioned that a variable, it's actually just a memory address. So let me just pick a random address here. So if I say, let's say somewhere here, starting at 0C100, and it goes to 0FFF. So somewhere here, let's just say that I want a variable at 0D100. Okay, let me zoom in a little bit. So 0D100, I'm going to place a variable there. Okay, well that's just a memory address. Exactly. So that means that this is a memory address, there's a number in there. So by default, let's say it was 0. Okay, so what's the point? Well, variables are things in our code that makes it easy to keep track of different things. So I showed you a power-up variable last time. So let's say that this variable was my power-up, but instead of remembering 0D100, I just call it power-ups, like that. So from now on in my code, I just need to remember the word power-ups. I don't care about the memory address, that's up to the assembler to figure out. That's not my responsibility. So as a programmer, I just remember this word, power-ups. Where it's placed in memory, that's not our concern here. So, what can we do with variables? Well, like I said, we keep track of everything. So let me make another one down here. I'm going to call it player lives. And this is going to keep track of how many lives I have. And again, it's just a place in memory. It's one memory address. And one memory address can hold 1 byte. So for every variable, we take up 1 byte of space in the Commodore 64 memory. So in this case, I take up 1 byte, 2 bytes. And for every variable that I add in my code, I'm going to take up 1 byte for every variable. So we keep track of everything, like player lives, maybe we have some ammo, whatever we need to keep track of. So the important thing is that variables can change. And obviously we know that already, that we can change the contents of a memory cell. We write LDA to load a number into the accumulator, then STA to store that number at a specified memory address. So that's no different here. So how does this look in code? Well, let's take a brief look at that. So now let's learn something new. When we're starting our assembly code, and this goes for kick assembler, what we're using here. There are a number of different assemblers, but let's not get into that now. But in kick assembler, what we're using right now, we need to start by writing basic upstart 2, all in one word. Capital B in basic, capital U in upstart. And in parentheses, I'm going to write main. And then I need to write main down here as well with a colon. So this will always be the start of our code. Now exactly what this means, we don't need to worry about too much right now. But this is how we start our code. Basic upstart 2, main in parentheses, and then main colon. So under main here, that's where our actual code starts. And another thing, when we're making code or a game for the Commodore 64, this thing right here is going to start at memory address 0801. So if you remember that the free space that we had, the 39,000 bytes, 39 kilobytes, the free area, that starts at 0800 or 0801 actually, which means that our code here starts at 0801. Now when I write 2 slashes like that, that just means that whatever comes after it is a comment, and it will not be a part of the code. So we can write as many comments as we want. But that's where our program starts in memory. So we don't start at 0000, we start at this address. Now the reason for that is that the first part here, as you might remember, that's occupied by the Commodore 64. So everything up to 800 is sort of off limits for us. Now there's a very special area here from 400 up to 800, and that's the screen memory, screen RAM. Now exactly what that means, we need to come back to that. The point is right now that our code starts at 0801. And that's, as I said, that's the default when you start writing code. And most games, I think, start at that address on the Commodore 64. Alright, but we are going to talk about variables now. So let me just remove this to make it less confusing. So right now I have an empty code right now. So I could write something like LDA hashtag 54, load 54 into the accumulator. But let's set up a variable first. So I'm gonna go a little down here, and I'm going to make my first variable. So let me make the variable player lives. I just write player lives like that, and a colon. Then I just write dot byte, and I'm gonna write 0 like that. So right now I have created a variable. this is my variable player lives. So I just write the name of the variable, colon, and then after that I write dot byte and a 0 in this case. So when I write dot byte here, that means that this is going to take up 1 byte, and that byte is going to be 0. Now, I could have any number in here. You can think of it as the starting number. So if you wanted the player lives to start at 3, for example, that's no problem. We can set it to 3 from the beginning. But right now I'm going to set it to 0. Okay, so now I have a variable called player lives. The question is, where in the memory is that variable right now? Well, if you look at this, I said that our code starts at 0801. That's where our code starts. That's basically what this thing does. So I don't have anything in front of my variable. I don't have anything here, which means in this case the variable is at 0801. Alright, well, we're not making the perfect code right now, so this is just an example. But I couldn't run the code like this, because just having a variable like this, it does nothing. And in fact, when I don't have any kind of code here in front of it, the Commodore 64 is going to think that this is a command. It thinks that this is an opcode, because when we put our code into the Commodore 64 and try to run it, it's just going to start at 0801 and it's going to run whatever is in there. So if we don't have a command at the very beginning, it's going to run whatever's in that address. And in this case, that's my variable. So instead of doing that, I'm just going to make a little loop here. So I write loop like that. And by the way, this is something called a label. So when we write a name like that and a colon, that's a label. And just like our variable down here, that's also a label. But labels are basically something that we use instead of using memory addresses. But in this case, I'm not going to write byte after this. I'm just going to write something else. I'm going to write JMP loop. So we haven't talked about this opcode yet, JMP, but it means jump. So when we write JMP, we're going to jump to whatever we specify after the JMP. And in this case, it's loop. So our code is going to jump up here to loop, which means that right now we have an infinite loop. So this program I could actually run, but nothing's going to happen. It's just going to go in an endless loop like that. So, all right. Let's do something interesting here. Let's actually make something happen. And then after that, let's get back to the variable. But just to demonstrate how this works, I'm actually going to introduce a new opcode here. Sorry. INC. INC stands for increment. It's the same as increase. So when we write INC, we increase something. What are we increasing? Well, we are increasing a memory address. So we need to specify a memory address. Let me show you. I'm going to write D020. This is a memory address. So when I write INC like this and a memory address, this is going to increase whatever value is in this address. So if this memory address has a 5 and we run this inc, it's going to be a 6. So let's remove that for now. Let's just focus on this right now. So here we have a very basic program. Basic, but we have a very fundamental program. So we have our main, that's just the start of our code, but I also have a loop here, and inside my loop I increment or increase whatever value is in this memory address. After that I loop back up here, and then I increase the value again, loop up here, increase the value again, and it just goes on like that forever. So what is this memory address? Why exactly that memory address? D020. This memory address, by default for the Commodore 64, this is the memory address that keeps track of the border color of the Commodore 64. So the Commodore 64 has a border around it. By default, that's light blue, if I'm not mistaken. So what I'm saying right here, increase the border color and jump up here and do that all the time. Just increase the border color. So the border color is going to change. So let me save this as main.asm, and now I'm just going to run this just to show you our first running Commodore 64 program. So what we're seeing right here is a program running or the emulator running our code, and it's changing the border color, but as you can see, it's not a flashing color. It's just this weird, very weird pattern. So what's happening here? Let me exit that. What's happening here is that our code is so fast that it's updating the border color just every few microseconds. It's happening so fast that it happens many times during one frame. So our code is I don't know if I can say 1,000 times, but it's so much faster than the updating of a frame. That's why we have tons of colors for the border color. So if I were to remove this, and instead of having a loop like that, I just write LDA hashtag and a number. Now the Commodore 64 has 16 colors. It can use 16 different colors. Every one of those colors has a number, and I happen to know that number 1 is the color white. So I'm going to load A with 1, load the accumulator with 1, then I'm going to store it in D020, and then I'm just going to have an empty loop after this. So now my code says make the border color white, because we load the accumulator with 1, which I happen to know is the color code for white, and I store that into memory address D020. And as I said, D020, that's a special memory address. That's not where we'll store our variables. This memory address keeps track of the border color. So let me save this file and run it. And there we go. Now we have a white border color around our screen like this. So this is a little off topic since we're talking about variables, but I just wanted to quickly introduce you to assembly programming. So let me remove this now. Alright, so actually let me remove this loop as well. So let's go back to the variable. So I'm going to write player lives like that, and again dot byte after that. And you know what, let's set it to 5. So what I could do right now, I could load my variable player lives, and this doesn't make much sense really, but I could store that value into D020. So let's try that. I'm going to LDA player lives. So I'm loading the value into loading the value of my variable player lives into the accumulator, and just for fun I'm going to store that into D020. That means that now the border color is going to be whatever color code 5 is, because number 5, that's what's in my variable. So when loading variables, we just use the normal LDA and the variable name. Now, it's very important, we don't use a hashtag in front of a variable name, because if I did that, then this wouldn't make any sense. So remember that we could use a hashtag for an actual number, right? But I also said that we could write LDA and a memory address, like for example 1000. And when we do that, we don't use a hashtag. When we're loading a memory address, then we don't use a hashtag. We want to load whatever value is inside that memory address. And that's exactly what we're doing up here. But instead of writing the memory address, we are writing the player lives, the name of the variable. So that's important to remember, that when we're working with variables, we don't use a hashtag in front of it. Alright, so I'm loading my variable player lives. I'm storing it into D020. Now I need to end this code with something, because if not, then the program is going to continue, and then it's going to try to execute this number. I don't want that. So here's yet another opcode, RTS. RTS stands for return from subroutine. That's also something we will be coming back to, but in this case, when we write RTS like this, it's basically just going to exit our program. That means it's not going to crash or anything when it gets down here. We're going to finish, close our program in a neat way, so we're not going to have any problems. But before we close it, we load our variable player lives, and we store whatever was in that variable into D020, which is the memory address that keeps track of the border color. Alright, let's try this. So now the border is going to turn into whatever color code 5 is. So let's run this little program. So color code 5 was apparently green. Alright. So hopefully you see what variables are. It's not really complicated. All a variable is, it's just a memory address. But as I said, instead of using the actual address for that memory cell, we just give it a name and then we use the name, because we don't really care what memory address it is. We just need it to be one memory address, because we want to have 1 byte to keep track of something. Wherever that is in memory doesn't really matter for us. So that's variables. What about constants? Well, constants is almost the opposite. And it's the opposite in the way that variables, they can change. We can update variables. Constants, as you probably can hear from the name, that's constant. It can't change. So, when I write, there are actually 2 different ways to make constants in Cake Assembler. One way is to write dot const and something after that. We're not going to be using that method. We're going to be using something called label instead. Now, I don't want to get into detail of what the difference is. Let's just remember to use dot label when we're making constants. So I'm going to write, let me just write white, color white for this one. I'm going to write equals 1. So now I have made a constant called color white. And another thing, let's also be very tidy when we're naming the different things. As you can see here, my constant is all uppercase letters. When I made my variable before, I wrote it with lowercase. So I like to make a distinction, but this is personal preference. It's nothing technical. But in order to keep the code looking neat and tidy, I very much prefer to have a set way of doing things. So when I write variables, that's lowercase, constants, that's all uppercase. But as you can see here, my variable name is made up of 2 words. So the way I do that is just by making the first letter of the second word a capital letter. You can't do this. You can't have spaces in these names. You can't do it with variable names. You can't do it with constant names. So we have to avoid using spaces in the different labels we make. But variables, lowercase, constants, uppercase. That's my personal preference. You don't have to do it that way, but that's how I prefer to do it. Alright, so back to the constant. Dot label is what I'm going to use to make constant. In this case, color white. So I just write equals 1. And that's going to be a constant for the rest of my code. This can never change. So I can't say increase this thing right here. That doesn't make any sense because labels can't be changed. So how do we use a label? Well, we write LDA, for example, but now we need to write a hashtag and color white. So why do we need a hashtag now and not when we were using the variable? Well, the thing is that this constant, that's just it's just another, it's a label so that we can use instead of using a number. So what I'm doing right here, I'm doing exactly the same as this. This means this. So in my code, I could write this LDA hashtag color white, or I could write LDA #1 and the result would be exactly the same. So again, we use these things to make it easier for ourselves. Instead of remembering a lot of different numbers, it's so much easier if we just give the different things different names. Names that make sense to us as human beings. So now I'm loading color white. Oh, sorry, I deleted it there. That. Okay, so now I'm loading my constant color white into the accumulator. And I'm going to store that into D020. And like I did before, I'm going to end my program with RTS. So now I'm going to save this and try to run this. Just like I expected, the border color turns white. Not because I called this thing white, but because my constant is number 1 here. So that's the color code for white. I could name this nice color or whatever, and that would be exactly the same, right? So this is just a name. We could write whatever, but it's a good idea to write something that makes sense. So the important thing here is that constants, when using constants, we need to use a hashtag because a constant is just a number. A constant is not, like you see here, we're not going to use that as a memory address, in this case at least. So constants can't change, variables can. Player lives. So this is a constant, this is a variable. So it might be a little it might be easy to get confused about this, but actually it's really simple. A constant is always going to point at whatever we specify as a number behind the equal sign here. So this can never change. I say once in my code, a nice color is 1. And that's true for the rest of my code. That's never going to change in my code. It can never change. For my variable, that's, as I said, almost the opposite. So this is just a label for a memory address. So instead of writing this, as we talked about, I could have written a memory address instead, and would have had the same effect. So now, let me just change it back here to color white. So it makes more sense. So we have this constant called color white, which is 1. It's going to be 1 forever. We have a variable, player lives, that's 0 right now. So what if I load my constant color white, store that into D020, the border color? What if I also load player lives and store that into memory address D021? So D020, that's the border color of the screen. D021, that's the background color of the text. So now I'm going to change the border color and the background color. So I happen to know that 0, that's the color code for black. So now I'm loading my constant color white. The constant color white, which is the number 1 here. Storing that into the border color. So now we're going to have a white border. I'm loading whatever is in my variable player lives, which is 0, so that's black. I'm going to store that into D0 to 1, the background color. Alright, let's try to run this. Did I do anything wrong? Let's see. Unknown symbol, player lives. Player lives. Oh, capital L here. So we need to I got an error message here that it didn't recognize player lives here because I had written player lives with a lowercase l down here. So capitalization is really important. Alright, now let's try to run this. Exactly like I expected. A white border color and a black background color. Alright, so constants, it's never going to change. Variables can be changed. So I don't think we should go too much into detail. Hopefully this makes sense. However, there's another thing, really important thing that I need to mention. I said that variables do take up space in memory. Why? Well, because a variable is in fact an address in a memory, right? We talked about that. So for every variable name, that's an address in the Commodore 64 memory. So if I have 5 variables, that's 5 places in the Commodore 64 memory. 5 memory addresses. So that obviously takes up space. What about this constant? Well, the constant doesn't take up any space. Why? Well, because the constant here, that's just something I make for myself. When I run this code, the assembler, which turns my code into binary code that the computer can understand, this, wherever I used this label, color_white, whenever in my code I used that, the assembler is going to replace that with whatever number I specify behind here. So when the code is finished assembling, there's no constant color white in there, because everywhere I used this constant name, that was replaced with the number 1. So that the computer doesn't need to keep track of anything called color white or anything like that. We just replace whenever we used the name of the constant, it just gets replaced with this number that we specify behind there. Hopefully that makes sense. So constants don't take up any space in memory. Variables do take up space in memory. As I said, hopefully that makes sense. Alright.